So let's begin our discussion of vector calculus by looking at what's called the del operator, and then we'll apply it to the gradient. Well, first we got to talk about vector fields, and just to remind you that if you have a vector at all points in space and it's associated with those points in space, we call it a vector field. It's easiest to see this in two dimensions, but in reality we have lots of three-dimensional fields. For example, the flow of air in the wind is three-dimensional, and so on. What we're talking about is the flow of a fluid, so water or air. Let's think of a simple case which is two-dimensional, and that is a form of symmetric flow along a surface where the velocity increases with the distance from the origin. One big question is, how could that happen physically? We have to have a source. Suppose that the source sprays fluid out of a nozzle that sprays in all directions, so radially. Let's suppose there's some attractive force accelerating each portion of the flow, and I put question marks in it because that sounds kind of silly. For this symmetric flow, every point in the xy plane has a vector associated with the form like this. It has a Vx component and a Vy component, and of course Z component is equal to 0. What might this function for these two terms, for these two components, look like for the case where we have this symmetric flow? Well, the answer is it's radial, and so one example of this would be a vector that's proportional to the r vector, some proportionality constant k. And so as you increase r, the magnitude of the vector increases. So this is a function, but the components are vectors. R lies in the xy plane, and so this would serve as an example. So let's take a case where we have a positive k. We simply take the r vector in the Cartesian coordinates. So r is equal to x hat plus y hat. And I've taken k equals 1, and I've used Mathematica to use vector plot to plot this out. And this is what it looks like. At the origin, x and y are 0, so you have 0 length. As you increase r, this gets longer and longer, regardless of what direction you flow. And that's because the vector itself is only dependent on the distance, and its direction is in the same direction as the r vector. So here's the deal. For this vector here, it originates at this point right here. Its length is proportional to how far you are from the origin. The vector which is pointing at the point where the vector is evaluated is r. So here's r. This is r vector. That's the argument for v. This is v here. The r gives you the point. And so that's true of any origin of these vectors. So, for example, this one over here, r would be the vector that connects to the origin. And the further away we are, the longer this vector. So this is a vector field in two dimensions that satisfies the definition of a vector field because every point in this space has a vector associated with it. Going back to the picture of what I just said, so here's your r vector, here's the point that's related to the end of the vector defined by r. This is v, and in this case it's radial, pointed here, and that will depend on the magnitude of k times x, and the y component would be k sub y. This picture here is just for one point, what I've already described. For a positive k, you have an outflowing field. So the field shows arrows associated with points in space, in other words the r points, to a point in space that then gives you the vector components that depend on x and y. And I claim here that they hang on the point. In other words, their tails are at the point that you're interested in. That's just symbolic. And they do not start at the origin. So in other words, the vector v does not start here. That's the vector r. These vectors all start out in space at some coordinate. And in this arrangement here, there's a source at the origin that gives us then this radial behavior. And the fact that the flow increases with speed means that we have to have some fancy force that increases with distance. Well, what if we just turn the k around, so we use k equal minus 1. Vector plot simply just reverses the direction. So this here would be the vector r to the point xy, and the vector capital V would be pointing in the opposite direction to r. And of course the length of this vector will be greatest at large r, and it will be 0 right at the origin. And that's what you see here. Here's the origin. The vectors get tinier and tinier as you go here, and they get bigger and bigger as you go out here, and the direction just simply reversed in order to flow towards the point. This kind of behavior would be described as having a sink here, and the flow is flowing into the sink, disappearing basically. The velocity is slowing down, slowing down, slowing down. Is this a physical possibility? Probably not. You'd have trouble with the fact that you have more material flowing into this region than could flow out the hole. So now let's talk about the del operator. This is a vector operator. It's written usually in this form here. Sometimes we write the word del. In Cartesian coordinates, this is the way del is defined. It is the unit vectors times their corresponding partials. I've written it this way just so that we can see that if you operated on something, you wouldn't have to worry what order these are sitting. It would immediately take the derivatives of whatever you put here. Okay, so the first thing is, notice that this is a vector. We can also write it as follows. We can replace particular unit vectors with e sub I, and we can take the derivatives with respect to x sub I, and the repeated index means to sum over I. Okay, so if we take e1 to be x hat, e2 to be y hat, e3 to be z hat, and then of course this is x1, this is x2, this is x3, then we have the same form, and it's just easier to write it in this form. Let's talk about the gradient. Here we're talking about an operation on a scalar function, and so let's just for now call it phi, and it's a function of x, y, z. If we consider that initially as a function of r, so some position vector, then it's a function of x, y, z. So this statement, these two are equivalent. So we take the gradient of this function, and we're going to take it in Cartesian coordinates. We can either write it grad or in this form here. And what we mean by that is exactly what we have up here. Here's del operating on phi. You take the derivative of phi with respect to x, with respect to y, with respect to z. And the fact that the unit vectors are here implies that this indeed is a vector. For another function u, which is a scalar function of x, y, z, we can suppress the writing of the variables just like we mentioned above. So if we take the gradient of u, this would be our operator, which is the sum over I, operating on the function u. Just putting this into the brackets here, so we just go past the unit vector, you can see that you've got these derivatives and then the unit vectors. And so we've slipped u around the e. This expression here is exactly the same as this if we call phi u. So what is the interpretation of the gradient? First of all, the gradient probes the rate of change of a scalar function in the three coordinate directions. So that's assuming you're taking this derivative and you have a function that depends on x, y, z. As a vector in 3D space, it represents the rate and the direction of the most rapid rate of change of the function, with changes in the coordinates x, y, z. I would just mention that for things that run downhill, like objects responding to gravity, the pull of the force and the motion that results will be in the negative direction of the gradient. Well, let's take a case where we have a scalar function throughout some space, x, y, z space, and we'll assume that it is unchanging with time. That could be temperature. Consider a room in which the temperature is given by this scalar field, and so at each point x, y, z, the temperature is T of x, y, z. So at each point in the room, the gradient of T, which is equal to grad T, at that point will show the direction in which the temperature rises most quickly. So what this does is the gradient determines how fast the temperature rises in the direction of the gradient. So suppose you have this function, which is just something I made up, and let's find the gradient. So all we have to do is perform our operation of taking the derivatives. So we would then have this operator operating on this temperature, which is dependent upon x, y, z. And so I've just gone ahead and done the operation. You can do it yourself. And so you have a x component, you have a y component, and you have a z component. Notice that these all have functional dependencies on x, y, z. They're different, but they do in fact depend on x, y, z. This is a pretty difficult quantity to conceptualize. It's easier to go to a 2D function. And so let's look at this function here. So we have a function of x and y. Again, just out of the hat, we choose this combination. So it's the value of y, and then the exponential of minus y times 5 minus x. We can plot it. We're going to let the z-axis actually be the function itself. So here's a simple Mathematica code for doing this, and here are the results. I'm able to rotate when I'm in Mathematica, so I wanted to show you different views of the function. So what you see here is a function which, if we go to larger y and small x, we have the function changing very little back here. It's almost flat. However, as we approach larger values of x and go and scan y across here, we actually get this dramatic increase. Just in this space here, you can see a maximum at this point right here. So as you go away in the smaller y direction for any x, you have this little bit of a hill, and then it falls off as you approach y equals 0. So here's another view of it, the same thing. So this maximum point is right here. This point right here corresponds to this corner here. And so you can see it's a little bit complicated, but it has some interesting features as a function of x and y. So we've got to think about what this means, this plot. Sometimes people get this confused. What we want to emphasize is this is a 2D scalar function. It only depends on x and y. There is no z coordinate in the function. What we let happen is at a particular point, x0, y0, or the plot of this thing is actually the value of f at x0, y0. What I want you to think of is that you are living in flatland. You're living in the xy plane. But to see what this function does, we use a 3D plot. If we pick a point right here, so this is our x0, y0, and evaluate the function, then if we just go up here to the curve somewhere, when it touches that curve, that's f of x0, y0 if this is x0, y0. Okay, so I think that's clear. What I want you to realize, there is no z coordinate. This is just the xy plane where everything happens. If we take a look at this then, a way to understand this function in a different fashion is to stay in the xy plane, but plot what are called contours. And what they are constant values of the function. So if you start at a given point, let's say you start right here, and you change x and y, but you keep the function constant, then you travel along this way, or if you go in this direction here, you'll stay on this line, and it corresponds to this function staying constant. This may be difficult to see because of the turning of the axes, but it looks to me like the maximum is right here. Here's the maximum of the function over here. Suppose you take a path right along this, what looks like sort of peaks in the contour plots. What you're doing is going down the maximum value of this function on the ridge of this distribution here. If you then were to take planes and cut this function, then you would find that you were forming a plane here. This is supposed to be a flat plane. So you cut this thing through there. The intersection of this plane with the actual function would give you one of these curves. For example, if you take this point right here, that corresponds to this one, and let's say we're outlining this contour here, then as you go through here, through this plane here, you will find there will be a curve that gives us this intersection right here. So let's, for example, go to a simpler case where we just draw a little plane up here like that. We only have to have a little plane because it's only cutting this function over a very small area. So for example, this plane here, intersecting this curve here, would give you a curve that looks like this. So let me just try to see that. Maybe we can see it over here. If we have just a little plane like that, so we're doing this like that, and ask where does it cut, it will cut right along there, like that. That little thing there is this little thing here. So I think you can see that you can make contours by changing the level of the plane in this direction here to get various values, different values of the function, so that if you set this equal to 0.1, 0.2, 0.3, you're forming the contours along here. If we're over here, in this region here, f of xy is nearly constant, so we really have no change to plot here. There's a certain sensitivity in the program, but there's very little change in the function back here. Whereas over here, fx and y is changing very rapidly. It's going up, and so therefore you have contours that are changing very rapidly. So you notice that the numbers, this is 0.325, 0.25, 0.2, 0.12, 0.05, so we're going down these values of the function. If we take the gradient now, this is the gradient in vector form, so here's the x component of the gradient, this is the y component. Because f depends only on x and y, the z term in the gradient is equal to 0, because there's no z dependence. So here's the gradient. Again, I just write it down, but you can form that differential very easily. This is the derivative with respect to x, derivative with respect to y, period. Those are the only two terms. So here's the first term, and then here's the second term. And because we have curly brackets, and because we have two components, that justifies our saying that this is a vector function. And it's a vector function in the xy plane. It only has x hat, y hat unit vectors. Well, there's a way to plot a vector field in 2 dimensions, and that's what you see here. This plot is the gradient. It's very uninteresting out here because the function is pretty flat, so you don't have any gradient. As you approach regions of steepness in the function, so you notice that it's steep here, so you have big vectors and they're pointing up the slope of that hill. And then over here you have steep large vectors because of the way that that curve is increasing. So that's the representation of a two-dimensional vector field, which we call the gradient of that function. Before showing this, let me go back to the function and remind you that we have the gradient very large along this edge here because of this function changing so rapidly here, and it's fairly large here because it changes quickly, and in this direction here. So let's go back to the gradient, and you can see that you have large changes here, large changes here in the regions where the function changes rapidly. The direction of the arrow is telling you which way is the change the steepest. Okay, so now I want to show you the two together in terms of the contours here and the gradient. So you'll notice that if the contours are very, very close, that represents a rapid change in the function f of xy. And that's where the arrows are the longest. And notice that they're in the direction of the rapid change of the function. So here they're this way, and then over here they're this way. So let's see that. Here they're this way, and over here they're coming in like that. So that's the relationship then between the rate of change of the function, which gives you rapidly changed contours, which gives you big arrows, versus very little change up here and very little presence of any vectors because they're so small. If you had a magnifying glass, so to speak, you could see vectors here, but they'd be shorter, shorter, shorter. Another way of representing a vector field is with what are called streamlines. And I've superimposed the vector field, which are these short arrows here, and the streamlines, which are these uniform arrows and lines which stream along the so-called flow. There's no flow, but let's call it that. The way you get a streamline is that you start at some point, you determine which way the gradient is pointing, and then you continue to evaluate that, and that will take you along these lines here. So if you started over here, you'd evaluate the gradient, you just get the direction of the gradient. This does not indicate the strength. So let me repeat then. You have a streamline produced by just determining the direction of the motion at every point, So therefore you stay and form lines which are like the flow that might be going from the low values of the gradient to higher values, like that. So this is the way you can visualize the vector field. If we take this and look at the contour plot, you can see that basically these things are going like this. They're going up the hill like that. I'm trying to just take you into this region right here. Out here we can't see it because the contour lines were not changing enough to actually plot. So streamlines tells you what the gradient field looks like. If you are comfortable with that concept, this is the actual gradient. But you can see that if you were to this, you would get a streamline. So you're following the vectors, the tail to toe. That gives you the flow. Here's one here. You can sort of see how it goes like that. And then over here is the actual streamline that the program produces. Okay, so let's superimpose the contour plot and the streamlines. And this goes back to what I was saying, that the streamlines, first of all, go in the direction of the maximum rate of change if we started here. So it takes you up the function. Here's the high values of the function. Here's the low values. And so the streamlines just take you right up those values. But don't forget, you're in 2 dimensions. This is analyzing the function, which is a function of 2 variables. Over here, the streamlines, as we showed before, are like this. Notice that this one here that goes right along the ridge just happened to have caught it. So that streamline is following the ridge. Again, here's the vector field that corresponds to those streamlines. In principle, we could have put that on too, but I think it's clearer just to use the streamlines. So if we go back to our function and imagine that we actually now consider a certain type of 3D situation, we let the function be the height of a hill versus x and y. Let me first say that this could be a function of just 2 variables, and so it could be just like fx and y, and we could think of it that way. It's hard to because we walk on hills and we know that they have height and we don't think about them as a function. Consider the component of the force of gravity that is tangent to the surface of the hill. The force of gravity tangent to the hill would be proportional to minus the gradient of fxy. And so in terms of the contours, I have to turn them around, and so I just took minus the gradient and then took the streamlines. And so these are the streamlines that are point in the direction that would take you down the hill, basically. Think of this as being in the xy plane, even though if you were up here on a sled, you go down the hill. But the thing that's making you go down is the component of the force that's tangent to the hill. That tangent depends on the gradient, which is in the xy direction. So if you have a rapidly changing function in x and y, the gradient in the xy direction is larger and pointing in a particular direction. To find this force along the tangent, we can use the gradient to determine both the direction and the magnitude of that.